Personal note before we kick off this new season of Tech Shorts. I took quite a bit of time off this year to deal with a personal health problem, which was optic neuritis, which robbed me of my vision for quite a period of time. I'm happy to say that it's all got better and I'm on the mend, but it's really appropriate that as we start this new season of Tech Shorts that we focus a little bit on this first episode on how the technology that we work on in our community is actually impacting life sciences research. Obviously, I want to see somebody find a cure for my condition so that other people don't have to tread down this path. And of course, there's a lot of other conditions out there, a lot of other illnesses out there that are still yet to be solved. So thanks to science that I'm able to see and work and do what I am passionate about again. But let's think about where the next steps are coming from. And so today we're going to talk to Angel Pizarro about the work that we've been doing in the wider community for bioinformatics to lower the cost of compute and actually improve the greenness and the performance of the compute so that we can get more bioinformatics done. Anyway, onwards and welcome back to Tech Shorts. Angel Pizarro, welcome back to Tech Shorts.
Hey, super glad to be back. I'm excited for Tech Shorts to be started again and working for getting information out there to our community.
Now, that community happens to include a whole lot of people like you. Weirdo bioinformatician.
Previous me.
Previous you.
Recovering bioinformatician. Right. Yeah, there's a lot of folks out there who are doing large-scale bioinformatics on open data. You know, we've, as a community, have two things that are really awesome and I love being a part of. One is that we publish a lot of data for all of us to reuse to do new science. And two, we publish a lot of methods that all of us use to do new science on that data in a really nice circularly beneficial relationship.
And so that means things like, say, like the NF Core pipeline library, which that's a pretty cool resource.
Yeah, absolutely. That's a great example where a community got together and said, we're all trying to solve the same problem. And we're all trying to solve the same problem in using the same tooling. Let's just work together and not have to rewrite every single script from scratch and have something robust we can all start from and make quick progress with.
Totally. I remember Phil Yules telling me that, you know, within like hours of the full sequence of the coronavirus being made available, people were spinning up pipelines out of NF Core to get a lot of interesting work done. And of course, those were the vaccine makers who were doing that.
Yeah. And that was the power of the community. And once you put these tools in place, they pick them up regularly. And if you make it easy for them to pick it up, they will. Which led us to think about, you know, something else, some big thing that's happening in the global, just sort of compute space, which is this transformation, architectural transformation that is being led by, you know, at first the mobile industry by picking up low power, powerful processors, but then going into the HPC. So now we're starting to see a lot happening with these ARM-based architectures.
It's ARM chips for the win. There's like... I asked some of the people from ARM recently what the number was, and I can't remember what the number is. It is an absolutely stupid number of ARM chips that are out there in the world. So the economies of scale for these things are huge. Yeah. But also, I mean, one of the cool things about like ARM chips, they're designed to be low power. Like that, you know, if you're going to put an embedded chip in a phone or an embedded chip in a set of traffic lights. You know, you have to have those things being low power. Right?
That's correct.
And kind of by that genesis, we end up with these very high-performing, low-power CPUs for doing HPC, which is pretty cool.
It took a while to get here, right? I think it was a part of the community to push faster and faster technologies onto the devices we all have in our pocket that force the low-power CPU makers to be serious about performance. Whereas, you know, the traditional architectures came from not a scarcity of power, of energy. They came from a scarcity of being flops.
Right.
So they've always looked at the target of being a capable processor, and they still are, right, when those are available. Having said that, if you can have the best of both worlds, if you can have a cake and eat it too, I think that's the best. So,
absolutely. I mean, I remember going to SC years ago, and the ARM HPC community was kind of like
tiny
fringe dwellers.
Yeah,
we were the weirdos, right?
Yeah, absolutely.
We're no longer the weirdos, and for me, I think like a marker in that series. I mean, like the Graviton 4, really cool CPU.
Yep.
Grace from NVIDIA, amazing CPU.
Amazing. They're
and
both amazing.
You see the Grace Hopper machines turning up, and some of the big supercomputers that are being built. Simon McIntosh Smith has got a big Grace system.
Sure. And
Eisenbahn.
Fugaku
Right.
being at the top by itself. Just
right. So they're no longer
dominant.
fringe dollars, but here's this really interesting data point that we produced last year, we AWS, which I think is kind of, for me, this is the thing that says ARM is here in a really big way. And it was that most of the growth, like more than half of the growth in EC2 last year was Graviton processors. So you think about that. This is like our cloud regions expand daily.
Yeah.
We have trucks full of computers getting wheeled in every day. We deliver these things with forklifts. We deploy, I don't know, petaflops, maybe hundreds of petaflops of compute every month into all of our data centers worldwide. But last year, more than half of that growth was using our ARM-based processors, the Graviton,
which is absolutely
huge.
Mind-boggling. And folks don't, even as supercomputing, like, if you're a bioinformatics person, you're used to your, university resources, right? And then you may go to a supercomputing center, and your scale of what you think is big changes.
Yeah.
Because that's a huge, we're getting into exaflops, we might be going much, much bigger. Those are huge machines. And then you get to cloud service providers, right, which have by design a massive customer base, and the scale just absolutely explodes. So if you think that's big, think 10 times bigger, and that's the reality, right?
Right.
As somebody who's not involved in that community.
And I mean, all of that, that growth, like behind all of that massive growth is the truth that it turns out not to be that hard to port codes over, right?
That's correct.
Like to convince massive numbers of AWS customers to stop using an x86 instance and flip to an ARM64 instance. There's a lot of work that has to have been done to make that possible, to make that a seamless switch. And
that's correct.
Linux doesn't have the kind of Rosetta thing that Mac OS has got to make it invisible. No, I mean, Linux, Windows, etc., you have to port codes.
Yep.
You have to recompile them from source. You have to fix the problems you find along the way. And that actually requires an awful lot of tooling.
Yeah, so, going back to putting these two lines together, like if you have a community that can take up tooling easily, they will, right? If they're incentivized to do it. But then you have to have that tooling. And that's where we are today in bioinformatics and in ARM adoption. That we have to make it easier to be able to take advantage of these, low power, high compute potential, low power processors that we have in Graviton. And so we've been working with the community for a few years now about tackling those, upstream dependencies that would enable folks to easily pick up a NF core pipeline and run it where they are able to for the most sustainable per watt computing that they can get. Sometimes that's going to be an x86 processor depending on the application. A lot of times we're finding out it can be an ARM-based processor, instantly giving you very similar, if not like absolutely equal performance to some stuff that you might get from other processors, but at a much more sustainable both in terms of cost, but also in terms of just the environment and the per watt compute unit that you get.
And it seems to me, and I'm a armchair observer of bioinformatics, but it seems to me when I look at all this Given that bioinformatics has put so much work into abstracting the workflow
That's right.
into a workflow language, like into a domain-specific language, and then, using container sets and, things like, say, biocontainers drawn from Bioconda, using, all of that tooling underneath to provide the actual executable part of it, and then underneath all of that is, a bunch of tin that actually runs stuff.
That's right.
It seems obvious to me that if we can do enough work down on that tooling level down below, help get all of the Bioconda codes running on ARM, et cetera, it should be kind of invisible to the bioinformatician that they're running on ARM, right?
Yeah, that's the eventual goal. And, like all things, the devil is in the details. And so we ran into a few challenges in this initiative. One was that first step. Did this application, low level, sometimes or oftentimes written in a compiled language like C++, actually support the instruction set? And there were times, especially when we started early on, that we had to make upstream commits into the application itself to be able to compile transparently for the different architectures. And a lot of times that was literal single line changes of code, right? Like in the header that says, detect what architecture you're on and then adapt your compiler to support it. Right? But these are important things, these really low level details.
These are stumbling blocks.
It's a stumbling block from a core piece that is an optimized computation that everybody uses within either a Python library or NF Core or something else, CWL. There are other workflow languages out there. There's your Perl scripter that might be doing bash scripts and Perl scripts together, right?
We dare not speak its name.
They all use the atomic, that one tool. So that one tool is the first step. And
this is like dependency matrix hell, isn't it?
It's not hell. It is just what it is, and it isn't. But you solve it once, and suddenly you have a Cambrian explosion of people being able to do it. Right. So you go for that low-level thing. You see what is actually being used, which was great from the perspective of NF Core, because we see what the community is using. We see what the dependencies are. Then we can list them out and say, are these the things? What's the prioritized list of getting these things going? Right. We have a ranked list of this thing doesn't work, but it is used by 90% of pipelines out there. We should fix that. Right? And that's what we've done over the last few years. So and
when we say we, who are the we here?
So this is a collaboration between the NF Core community, the ARM community, and David Lacomber. Shout out. You are a rock star. You've been leading the charge on a lot of this, and you've recently retired, which is sad for the community. But you're still making upstream commits. So thank you, sir. Thank you, sir.
Yes, we love you for
this. we should have you on the program soon and expect that.
We're going to have and of course the Sakara folks.
The Sakara
have been putting in a ton of effort. Phil and all of those folks out of that community, right?
NF Core, Sakara, AWS, and ARM have all been, and the community at large have all been working together to make this thing a reality. And here's where we are at today. And the bioconda community, by the way, as a parallel effort, they knew ARM was a thing that they need to support, so they put in infrastructure pieces as they are building their recipes to be able to create conda packages, precompiled conda packages for different architectures, including ARM. So they did that work about a year ago, and then that gets picked up by upstream container platforms, whether that's biocontainers, whether that's the Wave and Sakara containers project. To, at the application level, have a portable binary that can go on different architectures. So the next challenge that we're facing, and this is where we are today, is that a lot of pipelines, because of data provenance and provenance of being able to run that pipeline reliably, pin versions of applications to the pipeline. They don't use the latest. This is a best practice, right? You should do this because you never know what's going to change, especially in academic software, between one version to the other. So you pin the version. So we're going through the pipelines now and looking at what the specific versions of the binaries are being configured in the default version of the pipeline to be able to update it. And sometimes we've found that it's a very clean update. You just update the version and everything works. Sometimes that's not the case. For instance, one popular application that I won't name deprecated a command line argument that is passed on to the application, so the newer versions don't work the same as the other one. So that's one. So if you update, you now need to revalidate, you get the same results, right? So we're in the stage where we're in pipeline updates for the configuration of the version, but also validating that the result is the same. So there has been down in the weeds compiler application. There has been infrastructure updates like bioconda that enable those applications to be built on and distributed on different architectures.
Yep.
We're currently in the layer of configuration and validation, but there was also work at the top that says basically platform distributions like Sakara containers or NF core pipelines themselves to update the possible profiles so that the informatics community can say, I'm running locally on a Slurm cluster. I need a profile that knows how to talk to Slurm partitions and submit my job. Or I'm running on AWS batch. I need a batch environment that is, the workflow itself. I need a profile that says I'm going to run in AWS batch. So we've been tackling at it from both ends. We're finally in the middle where we're tackling the profiles, the application versions, and the validation of the results. So CI/CD to make sure that the result we expect is what we get at the end. So it's pretty exciting. It feels like there is a light at the end of the tunnel.
Yeah, it does, because we're not too far away. I mean, it feels like I think we're
so
up in
close.
the very high 80s, if not maybe low 90s, in terms of the percentages of bioconda packages that will run on ARM.
Oh yeah, we're much higher than we're in the high 90s.
Right, and to give other people out there some faith that this is going to end soon. The kind of problems we're finding when it comes to porting stuff and getting it to work on ARM, these are not highly complex problems. David found a few, and because David is David, we sent him the really gnarly ones.
Yeah. Camel code, for instance.
Right. but like we've got some, Phil and the guys over at Sakara have put some pretty good instrumentation in to get us the telemetry we needed to know where to go hunting first.
Exactly.
And one of the first cases they found was a hard one for David, where he really had to dig into a kernel of an algorithm to fix it. But 99.9% of the fixes that need to be done are literally, these are compile time, command line sort of stuff, just to make sure that, that makefiles and CMakes and build scripts work. But most of it's pretty trivial stuff. And it's just kind of cat herding to get the pull requests put up into the
We're definitely in the herding requests, and and I think if there's a call to action for the community at large, it is now high impact but low complexity work. I don't want to say low complexity, because validating that the result is a result is actually a specialist. We're now in desperate need of folks who know the pipeline and the result that should come out of it, to validate that it is the result that they expect.
But
that's something that a compiler junkie can't do, right?
Yeah.
They are focused on, is this thing compiling? And then secondary, is it as performant as I expect? But performance and a result that is accurate are two different things.
Right. You needed to build.
We needed to build.
You need to get a binary out the other end that works. Then you need to make sure that it actually performs well and gives you a validated result.
And that's the thing.
That's the science bit, right?
Yeah, the science bit.
The science bit's
the most
working.
important bit.
But to give everybody, just to remind everybody of the why we are doing this.
Yeah.
Like, we want bioinformatics to be meaner, leaner, and greener, and like we know from like our deployments of Graviton that we can make stuff usually around about 40% cheaper to run the same code and get the same results, right? And that's our measure in the cloud. We see the same kind of results comparing, when we talk to our friends at NVIDIA and they're comparing Grace on-prem to other on-prem clusters built on x86, so ARM ARM processors are leaner, meaner, and greener, right? If we can chop 30 or 40% off the cost of doing bioinformatics, holy moly, that's a big impact on the world, right?
Yeah. I mean, cost is one thing, and especially in this funding environment, cost is a major one, right?
Sure.
I think that is going to be a driver of people's interest in porting applications. But we shouldn't forget the watts per compute unit.
Impact on the planet.
Impact on the planet is a huge motivator personally, and I think doing this transition and helping the community build this transition will help us all feel good and better about the work, the already important work that we're doing.
Totally. So we're getting pretty close.
Yep, pretty close.
We do need help.
We do need help.
And of course, people can reach out to us to find out where they can direct that help if they want to get involved.
That's correct. The other place to reach out is in the NF Core Slack community. There is an ARM64 channel.
Yeah.
If you want to be involved in looking at your pipeline or getting help for your pipeline to create those profiles, to update the versions of the applications and make some upstream module commits, that's the place. That's where you're going to find all the tooling and some documentation and all the, we're enthusiastically motivated to help you get this thing up and running.
Yeah. And there is a lot of good support from the community. And Dave Lacombe is still sitting there in the background.
Still sitting there in the background. He might be
doing
in a rocking chair as well. Instead of an office chair, he might be in a rocking chair.
He is going to kill you when he hears this. Hey, David, if you're out there, you're going to have to send us evidence that it's not a rocking chair.
Exactly.
Anyway, so if people want to find out more, I'm going to make sure that we put the links to all of these resources in the show notes. Probably the big one is going to be, if you want to get involved, go to the NF Core Slack, sign up to that, and get into the ARM64 channel and just say, hi, I'm here, how can I help? And the kind of help we need bioinformaticians who understand how to validate, how to do validation tests with bioconda codes. We need people who are, experts at build scripts and monkeying around in that place to do that. Bit of cat herding around managing the gazillions of pull requests that we've got to all of the little package maintainers where we just need to get little changes pushed upstream, right?
That's correct.
Is that it? Is there more help that we need beyond that?
I mean, there's always documentation updates to pipelines and other things that the NF Core community needs at large, or new pipelines. I think that there's a variety of pretty regular hackathons for the NF Core community. Reach out to Geraldine. She's a great community manager and developer advocate for the NF Core community. Again, the community is so welcoming. There's so much to do in this field, and a willing and able support network to help you do it.
This is one of those communities inside, what I sort of call the larger HPC community, where I always feel good about every interaction I have, because what they're doing is really changing the world. I mean, this is big, world-changing stuff. It makes me feel good, like the time I'm spending to help them, to support them, and to build things is just turning into something great.
Absolutely.
Right. And of course,
and nice people.
They are nice people. So come over and meet some more nice people. And help us all out. Because like I said before, if we can lower the carbon footprint of bioinformatics, it's a good thing.
If we can make it cheaper for you.
If we can make it cheaper for everybody to do bioinformatics, I actually kind of suspect everybody's going to do just more bioinformatics.
More, but
right? We know
it. Of course.
That's kind of that's the pathology of the HPC community. Anyway, this is really good. Thanks for coming in today and talking about it.
My pleasure.
Hi. If you're enjoying this, can you click that like button? Seriously, it'll just take you like 1 second, not even that. And if you really like it, click on the subscribe button over there. We'll let you know next time we make something.